Hello, I am Dr. Thierry de Vrijer and I will be your lecturer for part of this course. Welcome to the first video of the Solar Energy, Photovoltaic Materials, Devices and Modules course. In this course you will learn about the design, properties, advantages and limitations of a variety of PV technologies. In this video we will introduce the different PV technologies that we discuss in this course. As we explained in the first course, photovoltaic energy conversion occurs through the generation of a potential difference at the junction of two different semiconductor materials. A semiconductor is a material of which the outer electron shell, called the valence shell, is semi-full. A conducting material only has one or two valence electrons in the outer shell. For example, group 1 materials, which are metals like copper, silver and gold, are conductors. Insulators, on the other hand, like the group 8 materials helium and argon, have a completely filled outer shell, with all the valence electrons strongly bound. Halfway between the conductors and insulators we find the semiconductors. The various PV technologies we will discuss in this course are defined by the semiconductor material that is used as the absorber layer. Right in the middle we find the group 4 material silicon. The first successful solar cell was made from crystalline silicon, which still is by far the most widely used PV material. Crystalline silicon solar cells use boron and phosphor for the material doping. Nitrogen and oxygen are used for the chemical passivation layers, while aluminium is generally used for the electrodes. So why is this important? There are certain requirements for the large terawatt scale implementation of photovoltaics. The materials used for solar cells should be non-toxic, cheap and abundant. The abundance of the elements used is therefore important for the upscaling of the different technologies. Let's take a look at the abundance of the elements. In this graph, the y-axis or vertical axis shows the number of atoms per million silicon atoms in the Earth's crust. The x-axis or horizontal axis shows the atomic number, which is the number of protons in the nucleus of the atom. We now populate it with the different elements found in the Earth's crust. We can see that silicon and oxygen are the most abundant elements, while iridium is the rarest element. We can indicate different groups in the graph. The rock-forming elements are most abundant and can most easily be mined. With increasing atomic number, the elements become less abundant. The rarest metals are indicated by the yellow area. The major industrial metals are indicated in red. These elements have a global production of at least 30 million kilograms per year. The precious metals are shown in purple. These elements are rare and very expensive. Finally, there are the rare earth elements. These elements are much more abundant than the precious metals. However, these elements do not have the tendency to become concentrated in exploitable ore deposits. Therefore, most of the world's supply of rare earth elements comes from only a handful of sources. So how about the elements used by crystalline silicon solar cells? Just to get an idea of the relative abundance, we can draw this arbitrary line at 1 atom per 1 million silicon atoms. All the elements used for crystalline silicon are well above this line, and none of them are toxic, rare or precious. This is one of the major reasons why crystalline silicon is the dominant technology in the market. The research and development of crystalline silicon has been going on for decades. This is the famous chart of the National Renewable Energy Laboratory of the US, or NREL for short, showing the evolution of the best research cell efficiencies. The record efficiency of crystalline silicon has increased from about 14% in 1975 to a current record of 26.7% of Kaneka for an advanced crystalline silicon solar cell without light concentration. Crystalline silicon has seen some amazing progress in the last couple of decades. Meanwhile, alternative families of PV technology have progressed as well. We will continue our discussion of the different PV technologies in the next video with the thin film technologies. So see you back in the next video.